So now we move to the design of 4-bit binary subtractor. Um, uh, we've already seen how we can design a 4-bit binary adder, and now we have enclosed it in a box. And now we see how we can use this 4-bit binary adder to make a 4-bit binary subtractor. So we perform subtraction through addition in order to avoid the complexity with the borrow. So um, so therefore, uh, let's see, we are given two numbers, A3, two numbers A and B, and we have to design a circuit that um, that helps us subtract B from A, right? So in order to design such a circuit, the first step would be to take the 2's complement of B, and that would require two steps. First, we compute the ones complement of B, which essentially means we reverse each bit in B. That is, now this B becomes and subsequently we add uh, 1 to make it a 2's complement, right? So now this becomes 2's complement of B, right? And then we add this 2's complement of B to the minuend, which is given here, right? So we already have a circuit that could add two 4-bit binary numbers, which is given here. So if we can take the 2's complement, or we can devise a hardware that could take this 2's complement, then we can easily convert this 4-bit binary adder into a 4-bit binary subtractor. So in order to do that, we need to reverse these. Uh, First, we need to reverse these uh, uh, each of the bits in B, which we can do using the inverter. And next, we need to add this one, right? This one, which was so actually this one was not here for this purpose. So we need to add um, this one to make it a 2's complement of B, right? And then we add the 2's complement of B into the minuend. So this is what we need to do, right? So it is important to see that generally in the first carry is 0, right? So this means if we take this 1 here and make this first carry 1, then we will be able to add um, uh, we will be able to add this 1 into B without any extra hardware, right? So which means that this first addition will become uh, A naught plus B naught plus 1, which is exactly what we want. We want to add B naught plus 1 into A naught, right? So, so once we have figured it out, uh, uh, how we can convert this 4-bit binary adder into a 4-bit binary subtractor, let's move ahead and actually try to do that. So this is a 4-bit binary adder, which we developed in the previous part of this lecture, where we use 4 full adders connected in series. So here, first thing that we need to do is to invert each of these bits in B using an inverter, right? And the second thing that we need to do is to make this or to make this the initial carry 1, right? So now, as a result of these modifications, this circuit now will perform 4-bit binary subtraction. Don't forget to discard this carry in case of subtraction. Um, so, uh, so here in this case, this would become difference, 0th bit of the difference, first bit of the difference, and the second bit and the third bit. So this is the 4-bit difference. This is how the 4-bit difference looks like, right? So um, so these are the modifications that are required to convert a 4-bit binary adder into a 4-bit binary. Now let's generalize this circuit. Uh, so a XOR gate has a very um, suitable property that allows it to be used as an inverter if we set its one input to 1, then the other input would be complemented at the output, right? And in case where we use and in case we set the other input to 0, then in that case XOR will transfer the other input directly to the output, right? So it means that so just for your visualization, I will perform this. I will explain how it works. So A, B complement, and A complement B, and so when we set A to 0, um, so the output in this case would be B, because this part will become 0 and this part will become B, right? And when we set A to 1, this will become B complement, because this part will become 0, since this one's complement will be 0, right? So so it means we can have a generalized circuit that can be used for addition and subtraction with just a slight change. So so instead of using the inverter, let's use the XOR gate. So let's just okay. Now, uh, so in case of uh, subtraction, this other output, this other input of uh, each of these um, XOR gates should be 1. That is in case of subtraction. And in case of addition, this output should be uh, sorry. In case of subtraction, this input should be 1, and same is also the case for C naught. So C naught should also be 1 in case of subtraction. This means if we just connect this C naught to the XOR gates, so it becomes a very meaningful circuit where if we change this C naught to 1, we get um, a subtractor. In this case, the output would be here. Output would be the difference, right? And what if we set the C naught to 0? So when we set the C naught to 0, in this case, this XOR will not work as an inverter. Rather, it will directly transfer these binary um, inputs uh, to the full adder, right? So in which case we will have here we will have B naught and B1, B2, and B3. And in this case, this circuit will work as a binary um, adder, right? So now with just change of this input, we we can easily convert this to a subtractor or a adder. Where one, in case of one, it works as a subtractor, 4-bit, and in case of zero, it works as adder, right? So um, and in case of subtraction, don't forget to discard this particular carry, right? So this is how we can design a 4-bit binary adder subtractor. So this is a clean drawing um, of a 4-bit binary adder subtractor taken from your book, where this part of the circuitry um, indicates the overflow. So overflow arises when the total number of bits uh, in the sum uh, exceed um, the maximum amount of bits allocated for the sum, right? So generally in computers, we have 8-bit registers, and when we are adding two 8-bit numbers, the sum might go to 9 bits. For instance, in this case, we are adding two 4-bit numbers, and the sum in some cases uh, may increase to 5 bits, as in situation where C4 is equal to 1, the sum here is now of 5-bit. Similarly, in case where when we are adding two 8-bit numbers, the sum might increase to 9-bit number, uh, and that means the sum now exceeds the total number of set limit, right? The total number of set bits rather. So, um, so in this case, we need an indicator that tells us that the overflow has occurred, and we need an additional resource. So here the output C serves as a flag of an overflow, but a more critical problem arises in case of signed numbers, where the most significant bit denotes the sign of the number, right? In case of negative numbers, the sign is 1, sign bit is set to 1, while in case of positive number, the sign bit is set to 0, right? But these sign bits are processed same as the previous 7 bits, which um, contain the actual number. So when we are processing assigned bit numbers using this 8-bit adder, which the 8-bit adder which may have or which might have four 8 full adders. So in that case, the sign when when the sum of these 7-bit numbers expands to 8 bits, the sign bit is now changed to 1. Although this is not a sign bit, this is an expanded version. Like this is part of the sum of these two 7-bit numbers, and the sign bit has now moved to this location. But the computer might mistake it for the sign. So in that case, it is important to set a flag that tells us that now the overflow has occurred and sign bit has moved to the next location, right? And similarly, in this situation, where when we take a case of two negative numbers, so in that case, we also see a situation where um, the sign bit transfers to the next location, right? And this time, the transfer of the sign bit is not due to the uh, the addition has now expanded to 8 bits, but it is because the two sign bits are 1, and when we add them, generally, so its sum is 0, 1, 0, and the 0 comes uh, in the location of the sign bits, and the 1 goes to the next location, right? So so here again you see the transfer of sign bit to the next location, right? So in these two situations, or we, if you just look at it, it is very like it is possible to design a circuitry that could help us detect this situation. For example, if there can be only two possibilities, either the sign bit is changing because of the carry from the previous edition. If the carry from the previous edition is 1, in that case sign bit might change and the sign bit transfers to the next location. Or in situation where the the sign bit from the carry from the previous edition is 0, but since the two sign bits are 1, so because of their addition, the sum is always 0, and the carry is now carry at the next location now serves as the sign bit, right? So in both of these situations, you see uh, the carry um, to the sign bits and carry from the sign bits are different, and in both these situations we need to set the flag. So in these situations, the XOR gate um, works perfectly to set a flag where if C3 and C4, in this case C3 and C4, but in maybe in 8-bit adder, these might be C7 and C8. Uh, uh, so, uh, so the carry to the last addition C7 and carry from the last addition C8, or as the case may be, can be XORed to get the flag in this situation. When these two carry are different, it means the sign bit has changed and it has transferred to the next location. So this B flag then addresses this situation and serves as an indicator. So this is the design of this, and the design of 4-bit binary adder-subtractor and the issues related to it. So in the next lecture, we will see the BCD adder and binary multiplier.